Actually, I just thought for fun I would even show how a way that a human might think of how to find a formula rather than how some mathematical might find a formula, let's say. So if you put that into Mathematica and then said what's the simplest function that gives it, I'm sure it could sort of output the right quadratic with no trouble at all. But a more human way of doing it would be just to say, well, let's write down an expression for the nth term. So we have to add 2, then 4, then 6, and so on, up to 2 times n minus 1. But then we recognize that 2 plus 4 plus 6 is twice the sum of the first n minus 1 integers. And we know what the sum of the first n integers is because we just do, and it's n plus 1 over 2. So double that, we then n plus 1. We actually want to only go up to n minus 1, so it would be n minus 1 times n. Then add 41 to it, and we get 41 plus n minus 1. So there's our formula for the nth term, discovered in a sort of human way rather than, but that's just a little bit of an aside, really. So now the question becomes, is it the case that 41 plus n minus 1 is a prime for every positive integer n? And I think it's fairly easy to see the answer now, but let's just try and do it in a way that one could conceivably imagine a machine doing it. So we want a counterexample, so we've got to find some factor of this for some n. So we might think, let's just focus on what the factor might be. And then we might use the standard proof technique. Let's try the simplest thing. So could we try 2? So we might try 2, and we might observe that any 2 consecutive numbers, one of them is even. So n minus 1 is even. So when you add 41, it's odd. So it'll never be a multiple of 2. Okay, let's try 3. A similar argument shows that actually 41 plus n minus 1 can never be a multiple of 3 either. You might go a bit further, it can't actually ever be a multiple of 5. So these small examples don't work. So what do we do at that point? Well, there's another standard proof thing. You don't try and necessarily find the simplest thing, but you want to find something that's sort of relevant to the problem in some way. So we might be focusing on small factors. Is there a number anywhere around here that's sort of relevant to the problem? The answer is obviously yes. That number is 41. So 41 would be a very natural thing to see. Can we use 41 as a factor? And as soon as you can ask the question, well, what are we trying to prove? That there's 41 divides 41 plus n minus 1. That's equivalent to 41 dividing n minus 1. That means that I'm insulting even the computer's intelligence, you know, but what does that mean? You want to find n such that 41 times n equals n minus 1. And now really it's so much staring in our face, we can choose n is 41 and n is n minus 1. And we're done. And that's somehow, again, a very good, characteristically human way of coming up with a solution. But I still think there's the various different steps can be automated. Now those, I've not yet talked about some very important things. This is sort of what you might call a sort of post hoc justification. I've sort of told you the various little problem-solving tricks that led to the solution, and not talked about all the other tricks that I haven't done. That's very important, so I'll come to that in a moment. So yeah, that's what I want to talk about. There are lots and lots of different problem-solving devices. It's not enough just to show that those problem-solving devices can be used to solve the problem. You have to sort of discuss as well how you decide which one to use in a good, efficient way in order to end up with a solution. And then there's a second question, which is a bit more of a sort of lower-level technical question, which is once you've decided which one to use, how do you actually implement that problem-solving strategy? Which should, in theory, be an easier thing than deciding which one to use in the first place. But even the first component has 2 parts to it. So when you're considering a problem-solving device, there are a couple of things that are very important. One is how hard it would actually be, how much sort of effort it would take to apply that device. So it might involve, supposing you're solving something and you say, well, if I could solve this very complicated looking quartic equation, it might be helpful. But you probably think, I'd rather not try and solve a complicated quartic, even though there are formulas for quartics, because that would be just a horrendously horrible thing to do. So I'm going to search for other things first. The other very important aspect of the device is just how likely it is to be helpful if you go ahead and do it. And supposing you have some way, which this was obviously not going to be a straightforward part of this, because it seems quite sort of high level, but some way of assessing the likely, also what the properties of various problem-solving devices are. So you might sort of assess k different problem-solving devices. How do you actually choose between those k? Now, this one is not much effort, but probably isn't that helpful, and this other one would be quite a lot of effort, but you have a sort of 50% chance that if you actually go through that effort, it will constitute a significant advance in the problem. How do you judge between those two as the thing that would be most efficient to do first? Something I've been doing, thinking about with some undergraduates doing a summer research project over the summer, was connected with this, with that second question. So if you've got, supposing you had some oracle that could tell you how likely a particular problem-solving device was, or a step in the thought process was, to be fruitful and how much effort it would take. What would then be the best strategy for sort of finding proofs as efficiently as possible? We tried to model it using a game that we call Doors. I haven't described it properly, I mean, I'm just getting a rather informal description, but the rough idea is that you're in a house. The rooms of the house are supposed to be modelling sort of where you are in your thought process when you're trying to solve a problem. And then you have doors into other rooms. Those doors are telling you, so they're sort of modelling the problem-solving device that you might consider applying from the situation that you're in at the moment. And when you go into another room, that's sort of the new state of affairs after you've tried using the problem-solving device. And when you do use problem-solving devices, there's a distinction to be made between the probability that you're sort of on the right, between your assessment of how likely you are to be in a good state after you've used the problem-solving device, the assessment you make before you use it, and then the assessment that you subsequently make after you've used it. So, you know, you might think, if I can prove this lemma, it will probably be helpful. You prove the lemma, and then you try to use it, and you discover it's not helpful. So you have an assessment that you made beforehand, and then the assessment that you made afterwards. So we model that as follows. On each door, there's a sort of probability that if you go through there, you'll still be on the path to your destination. But when you get to the room, that probability can be revised. We have ways of sort of making that into a formal game. We thought about that quite a bit, hoping we could model to some extent the mathematical discovery process. It actually turns out that when you make a specific game along these rough lines, it seems to lead to very difficult mathematical problems quite quickly. So we found it rather hard to analyse any sort of game that we came up with. But I still think that, well, I think this type of idea would be something that would be quite worth thinking about, because I think something a bit like it, although with all sorts of qualifications about it, but something along these lines I think is important for understanding how human mathematicians make the sort of strategic decisions as well as they do, faced with the options that they have in front of them. So some of the complications that you might have with this game is how much of the structure of the house are you supposed to know when you're playing the game? How much can you predict what will happen if you go through this door? But when you're doing maths, you sort of think, if I do this calculation and it really simplifies, then maybe something along those lines will happen. And if that happens, then this will get hazier and hazier as you sort of look further and further ahead in what might happen when you try to solve it. So that sort of haziness would have to be modelled somehow and so on. I just thought I'd mention that in passing, because I think it just again gives some idea of the kinds of things that interest me anyway. Let's go back to the question of how you actually choose a good problem-solving device. I'll look at this rather simple problem that we had before. So we want to find an A. We want to find an n such that 41 plus n minus 1 is not prime. So we want to find an A and an n such that A goes into 41 plus n minus 1. So here are a whole variety of problem-solving devices that we could use. I'm now being slightly more honest, I think. I'm just saying there wasn't just one thing we could have done, there were a whole lot of things. And how might we choose between them? So some of the possibilities, you could look at a small value of n, and if you found a small value of n, you could try a small value of a. The other way around, you could say, let's take the smallest value of a and then look at the smallest value of n, which you haven't sort of ruled out some. Or you could take the smallest value of a and sort of just look at what that would say about n. Slightly more, slightly different approach from just searching for an n. Then there are three that are a little bit different. So you could try choosing an n that is somehow related to the problem, or you could choose an a that's related to the problem, or you could generalize the problems and say we don't really think 41 is important, let's replace it by an arbitrary integer n. All those are natural proof discovery strategies, and some of them are better than others. So let's just think about how we might assess them. So the first one is trying to find the smallest value of n that we haven't ruled out. But actually, we've already ruled out quite a few values of n. We looked at quite a number of terms in that sequence, 41, 43, 47, 53, 61, and so on. So that didn't seem to be getting us very far. They were all prime. So that seemed like a bad strategy. The smallest value of a not yet ruled out. That doesn't look terribly promising because after we've chosen the value of a, we would then have to choose the smallest value of n. And back to the problem that we had before, that we know that a lot of small values, the first few values of n just don't work. So that seems like a bad approach. What about the smallest value of a that we haven't ruled out and then examine the constraints on n? This looks a little bit better because so what we're saying is we take a number like a equals 3, can we find an n such that 3 divides 41 plus n minus 1? And that will work out as just a congruence condition on n, or on n minus 1. So maybe we can just sort of see whether that congruence condition can be satisfied. It seems like a fairly simple thing to do. But actually we've already thought about that. It didn't work for 2, didn't work for 3. If you actually check this, you find that you can't satisfy it when a equals 2, you can't satisfy it when a equals 3, you can't satisfy it when a equals 5, you can't satisfy it when a equals 7. After a fairly short time, one's assessment of the likelihood of this approach leading to a solution quickly, it sort of diminishes and diminishes. So it's quite rational, I think. This goes back to this Dawes type idea. It's quite rational to try 2, 3, and 5, and maybe 7. But to try everything up to 19 would be a bit silly. I think at some point, enough's enough. We're going to have to be a bit more theoretical. So here are the other three. Now, these are all quite easily shown to be quite easily seem to be good. So I'll just discuss them quickly. So choosing an n that's related to the statement, a natural thing to try is n is 41. And does 41 go into 41 times 40? We just see very, very quickly that it works. And we've already seen that choosing a to be 41 was also quite easy. And generalizing the problem by replacing 41 by an arbitrary integer m, that's also a good thing to do because it then sort of stops you doing anything that's sort of specific to the number 41 and forces you to think more algebraically, and then it sort of basically leads you very quickly to the same sort of answer, except that you'll choose n equals m or something like that. So all three of those are quite good and work quickly. So in general, there's one heuristic that says if you've got some slightly unpleasant number that doesn't seem to have any relevant properties, replacing or object at all in a problem, replacing it by a general object of that kind is usually a good thing to do because you get rid of all sorts of distracting information. It's helpful to get rid of distracting information because there's less you can do, so the search space in which you're searching gets smaller, which can only help. Well, it can only help as long as you were right, that there wasn't anything important in that specific example. But that can be a risk that's well worth taking, even if sometimes you're wrong. I just thought I'd very briefly talk about machine learning and whether a natural thought to have is if you're trying to produce a system that thinks like a human, you should use machine learning, because the whole point of machine learning is trying to, well, in some ways, think like a human. My own view, but I'm a little bit skeptical about that, though, in this context. My sort of view about this is that machine learning is sort of good for pattern recognition. I can instantly recognize my mother's face, for example, but if you asked me to tell you now, in detail, so that you would be able to recognize my mother if you saw her in the street, I wouldn't be able to do it. But if I told you that I instantly saw why this would be a good thing to do for this math problem, and you asked me to articulate how I instantly saw it, it might be a bit challenging to think of the answer, but with a bit of thought, I often would be able to tell you how I came up with the idea. So I think that's two very different situations, and I think machine learning is probably more suitable. I'm not saying with huge confidence, but probably more suitable for the kind of stuff that goes on that we cannot really analyse and articulate. It's not so obvious. It might have a role, but I think if one were to use it to decide on, so supposing you use some very big statistical approach to decide which problem-solving strategy to use in certain situations by looking at hundreds of thousands of proof discoveries and seeing what was used, and it might work, but I think it might be sort of reasonably efficient, but I would find it a little bit disappointing. Partly because of what I said before, that we would very much like a program that can actually explain what it did. A program that said, well, I just modified some weights in a neural network and this is what came out. It's not really telling me as a human mathematician how the idea was generated. So that's my view about that. Now, very briefly to end, I just wanted to talk a little bit about what I was doing with Mohan Ganesalingam. So we were looking at the lower level problems. So we set ourselves the task of writing a program. Actually, writing a program wasn't really the main aim. At first, it was just thinking about how it would be done. And writing a program was sort of just a way of sort of checking that our thoughts did actually, was the algorithm could be implemented, what we were thinking about. We wanted to solve routine problems in abstract analysis without any backtracking. So we defined routine to mean a problem that a human wouldn't backtrack for. So sort of problem where if you're giving it as a lecture, if you're giving it in a maths lecture, you don't have to have your notes in front of you, you don't have to sort of learn the proof, you just say, I know if I just do the obvious steps, I'll end up proving the result. So a good test for whether a program is thinking like a human is whether it can solve problems without backtracking whenever humans will typically solve them without backtracking. Of course, what one actually wants is much more than that, but this is a start. So what one really wants is a problem that can solve any problem that a human can solve, doing at most as much backtracking as a human would do, or something like that. But this was sort of, if you can't do the routine ones, then there's not much hope for the non-routine ones. So we started with this. And to get some sort of idea of whether the program is really thinking in a human way, just very briefly what we did actually in the end for the class of problems that we were looking at, it turned out that something sort of almost disappointingly simple worked, which was we had an ordered list of possible moves to make, and it just shows the first one that it was possible to do at each stage. But we thought quite hard about what order to put them in. And that, the very simple problems seem to reproduce quite accurately the way humans thought about the problems. And so, yeah, as I say here, we converted the output into natural language. So when I say fairly crudely, what I mean by that is so it would proceed in a series of steps. Each step we would translate into a sentence written in natural language in a fairly sort of simple way. If you just concatenate those sentences, then you get something that reads a bit oddly because it will sometimes make sort of odd repetitions from one sentence to another where a human would think it wasn't necessary to repeat that because the reader really knows. So then we had some ways of sort of slightly adjusting the write-up so as to avoid those infelicities, and that was it basically. So yes, just to finish, here was an example of a solution that it produced. So the question was, we've got a continuous map between metric spaces which show that the inverse image of an open set is open. And it produced a proof that was pretty similar to this sort of thing. An undergraduate might write if they were asked to do that in an exam, let's say. If you look closely, you find that these things, maybe it's a little bit too fond of the word whenever and things like that, but that was actually a sort of little thing of mine. But the point about this whenever was to avoid sounding a bit over formal and starting like, for all blah blah blah. But to make it more realistic still, one would probably want to bring the changes in some sort of arbitrary way. But we weren't so concerned about going to that level of real.
So is this produced by the computer or not?
Yes, it is. So this is exactly what it produced later on its own, and that's what it was. So it wasn't some formal language or some semi-formal thing that we translated into. It was precisely the program.
And completely automatic.
Yes. Just before I basically finished, but I have to say, so as not to give a false impression here. This was done some time ago, and we've slightly sort of both been doing other things for about a year and a half. So, and at the point where we left it, we had a few sample problems that it did well on, and each time we fed it some new problem, there would be some little tiny technical glitch that would mean it wouldn't do quite what we wanted it to do. So, but it always seemed to be a minor thing, and you say, oh yes, of course, we'll have to sort of adjust this over there. So I don't even want to claim that we have a system that for all problems of difficulty like that can produce proofs that look like that, because that isn't yet the case. But we've got far enough that it does look as though once we sort of properly get back to it and start tweaking it and so on, we should be able to get to a program that can do a lot of problems like this, and in particular to ones that we haven't already designed it, so that we haven't sort of already tweaked it to make sure that it's okay on those problems. So that's what I mean really when I started at the beginning, saying I don't really want to claim that we've achieved anything very much at all, but we do sort of have a kind of personal conviction that at some stage, I very much hope to make a sort of serious contribution to automatic therapy at some point. And this is sort of how I hope to go about it. That's sort of the spirit in which I'm giving this talk. Okay, thank you very much. Any questions for Tim?
Roman.
Okay, so are you familiar with work in cognitive science, cognitive modeling, going back to the work of Alan Noel and Simon on automated problem solvers that they use to, for example, solve dimension problems in algebra and generate solutions to events in the field? That goes back to 60s and 70s. Of course, maybe not.
So what was the names there?
Alan Noel and Simon.
Oh, Newell and Simon, yes, I do.
So they did systems like SOAR and AGA that were used to generate similar solutions to humans.
Actually, another name that I should have mentioned, I was going to mention them, I just forgot what I was going at. For problems in analysis, Woody Bledsoe, if anyone's knows about him, he's the sort of things he was trying to do very similar to the sort of things that we were trying to do. I would love him to, if I could go back in time and meet him, I would love to do so, because I feel as though he was very much a kindred spirit. But his school sort of seems to have died out somewhat.
No, every year there's a conference going to modeling.
I see, okay, well there are some people, yes,
Dijkstra produced a series of monographs
in which you follow through your program of trying to show that every step in the proof is dictated by the shape of the proof, of the previous lines of the proof and the goal of the proof. We need to eliminate, X occurs on the left-hand side, we need to eliminate it. The only axioms that we can use that eliminate in this context are these ones, so the next step of the proof is determined. Right. As a standard style. As a standard style.
Thomas.
Just a very simple question. So, for this sample out, what does the sample input look like?
Oh, yeah, okay. So, Mohan Ganesalingam has worked very hard with Tom Barnett now on a system that can take natural language, mathematics written in the sort of slightly formal natural language that you would get in a textbook. So a theorem as it might be stated in a textbook, compile it and everything like that, and could sort of convert it in principle into some slightly more formal thing. So actually we didn't try to sort of attach his system to this. So what it is, it's sort of just a bit more formal. It's something like, for all x and y, metric space x and metric space y, something like that. And for all f, for that function of x and y, etc. So it would be in a kind of, wouldn't be a symbolic thing, it would be sort of for all x, tag x and height of x implies, so it wasn't, the input was not in natural language, but it was, you can look at it and understand it very easily. So it's
So a question at the back? No?
Yes.
There.
You mentioned your scepticism of machine learning in this context.
okay, so that's not it's some mixture of skepticism and just sort of my hope for how things will turn out.
So I guess you had in mind stochastic pattern recognition of something like inverse entailment for heuristic influence, so good induction in effect. So there have been successful strategies in the past to infer new rules, generalizing as appropriate. It might be appropriate for machine learning in this context.
Yes, one of the things that seems sort of difficult is how the state of the problem would be nicely represented in such a way that your machine learning could actually learn. If you just represent it as a piece of text, I think.
They can be complex, it certainly would be difficult for stochastic pattern recognition, so it's not the only one.
Tess, did you have a...
Yeah, so I was wondering, you describe it as like a process of deriving one step from the other and maybe do some backtracking and so on. I suspect many humans jump around a lot. So they might say, okay, I have this lemma, it's probably quite costly to prove this lemma, so at first see if it gets me anywhere. Do you use something like that?
Well, I've got something that I think I didn't talk about. A concept that I find very useful, an informal concept that I find very useful to think about something, which I call a splitting question. So you've got a question that you're trying to answer, call it P. And then a splitting question, maybe a pseudo-formal definition. It's a question Q, such that Q looks as though it ought to be easier to answer than P. And P given Q looks as though it ought to be easier to answer than P. But P given Q means answering P given the answer to Q. So this is creating a dilemma. Q might be, is the lemma true? And P given Q might be, is P true given that the lemma is true? So then, if you come up with a splitting question, that might be a sort of the next step you might take. Or the next step would be either thinking about Q or thinking about P given Q. Sometimes one of them is so much easier than the other that you just quickly check it. But quite often in the situation that you described, where it's sort of slightly to keep people in the queue, like a little bit easier than queue, so you think about being in the queue first. Some of what I talked about with sort of problem-solving strategies is rephrased in terms of not always accurate, in terms of asking a different question. Asking the same question but replacing M by 41 by splitting question. In that case, if you can answer it for general M, then obviously you can answer it for 41. But somehow it seems easier for some reason.
I think we can take any more questions to the coffee break. Now the coffee's arrived, so thank you very much, Tim and Dan.